Welcome to Mathematics. Today we'll be solving the Pearson Edexcel IAL January 2024 paper of Physics Unit 1. Question 1, we need the SI unit of stress. Stress is force per unit area. So Newton per meter square. So this is the answer. We need to, in question 2, we need to select the table which only contains vector quantities. Acceleration is a vector quantity, momentum is a vector quantity, weight always has a direction. So if you have an object, its weight is always going to be downwards. So the direction matters over here. So weight is also a vector, as this is a force. In this case, density is not a vector. In this case, mass is not a vector. Time and work done are also not vectors. Here mass is not a vector, and in the last one, kinetic energy and temperature are not vectors. So A is the answer. On to question 3. We are told that a spring is stretched by applying a force of 3 newtons, and the elastic strain energy stored by the spring is 0.04 joules. So the formula for the elastic potential energy or elastic strain energy, just write elastic energy over here. This is half into force into extension. So this is 0.04. This is half times 3 newtons, and we have the extension here. If we calculate the extension, we'll get 0.04 divided by half into 3. So 0.04 into 2 by 3.0, which is this. So A is the answer to question 3. Now in question number 4, we are given that a cyclist moves along a horizontal road at a constant speed and then moves at the same speed up a hill with a constant gradient. So when she's on a horizontal road, this is the force diagram. She'll experience some resistive forces from friction and air resistance. So this is the resistive forces. So there must be an equal forward force for the acceleration to be 0, because we are given this is a constant speed, which would mean that the net force is 0. So if the driving force is here, D equals to R. So this option over here is out because we have a non-zero power over here. We need some power to overcome the resistive forces. Now we are told that she moves at the same speed up a hill. So something like this. This is the driving force now. Now the resistive force will be this R plus the component of weight down the slope. So if this was theta, this would be W sine theta. So D would be greater when they're on the ramp. So this option is out. So D1 equals to R plus W sine theta. R and W sine theta don't change, so they are constants. R is a constant here. So this part of the graph and this part of the graph must both be horizontal, because if power is increasing, it would mean that the force is increasing. But we know that R plus W sine theta is a constant. So this is out as well. We are left with this graph, so D is the answer. It matches our description. A constant force over here, a constant force over here, which is greater than before. Now in question 5, a student dropped a table tennis ball which fell for time t and had velocity v just before it hit the ground. Now we are told that they use the equations of motion or the Soviet equations to calculate t and v, ignoring air resistance. Now we have to select how the actual values would be different from the student's calculated values. So they're dropping the ball over here. So resistance to motion would be upwards. So the final velocity will be less than what we calculated, and the time will be more than what we calculated. So time is greater than calculated and velocity less than calculated. The time will be greater because the ball will fall slower, and the velocity will be less at the bottom because the force on the ball, the resultant downward force on the ball throughout the journey is less than before what we calculated. Now on to question 6, we are given a length of string which is attached between two vertical posts, and a bar of weight W stands on the middle, causing tension T on the string, which makes an angle of 80 degrees with each post. So we'll have two components of the tensions. So the vertical ones and the horizontal ones. This angle over here will be 10. So this angle over here will be 80 degrees again. So the vertical force will be 2t cos 80 degree, and this will be equal to the weight. So weight equals to 2t cos 80. Now we have to make t the subject over here, so we'll get W by 2 cos 80. This is the answer. In question 7, we are given that a force is applied to stretch a spring, and the graph shows how the length of the string varies with the applied force. We have to find the stiffness of the spring. Force is K del X, or force. In this case, we have the length of the spring over here, so we can make X is the we'll consider X to be the length of the spring at a given force minus length, which is the original length of the spring. We'll get this equation over here, F equals to Kx minus Kl. If we plot a graph of F against X, or force against the length of spring, this will be a straight line with gradient K and y-intercept of minus KL. So this value over here will be minus KL, and the gradient will be K. So this is our answer. The gradient of the graph will give us the stiffness. Now we are told in question 8, there is a solid cube of weight W made from material with density rho. We have to find the length of each side of the cube. So weight equals to mg. We know that the mass will be weight by g. Now we know that the density is mass by volume. A volume of a cube will be side squared. So side cube, its volume would be side cube. We know the density. We can replace the mass with W by G. So density is W by G divided by side cube. Now we have to make the side the subject. So side cube would be W by rho G. The side would be cube root, weight divided by density into G. So D is the answer. Now in question 9, we are given the stress strain graphs for two wires P and Q. We have to find which statement among here is correct. We are given four statements that P has a greater breaking stress than Q, P has a greater breaking strain than Q, P has a greater yield stress than Q, and P has a lower Young modulus than Q. We consider each statement at a time. So the first statement says that P has a greater breaking stress than Q. However, if we see the graph, the breaking stress of P is lower than the breaking stress of Q. So this is Q and this is P. So this is incorrect. Option B says that P has a greater breaking stress strain than Q. If we check the strain, the breaking strain of P is here, while the breaking strain of Q is over here. So the breaking strain of Q is more than the breaking strain of P. So this statement is incorrect again. Now statement C says that P has a greater yield stress than Q. This region is the yield stress. So this over here is the yield stress of P. This over here is the yield stress of Q. The yield stress is when the graph goes something like this. It's more over here. This is this and this. So for P, the yield stress is greater. So this is correct. If we check the fourth statement again, it says that P has a lower Young modulus than Q. Lower Young modulus would mean that the gradient is smaller. However, if we look at the start, the gradient of P is more than the gradient of Q. So P has a greater Young modulus, which is contrary to our statement over here. So for this question, C is the answer. Now in the last MCQ, we are given that an object moves from rest with uniform acceleration for time t. We are given the acceleration time graph over here, and x is the area under the graph. We have to find what's the distance moved by the object. So if this is the acceleration time graph, the velocity time graph will look something like this. We know that the area under the graph for at will be the velocity. So since the acceleration is constant, velocity will have a constant gradient, and this value over here will be x, and this will be t. This is the VT graph. The area under the VT graph, this area over here, is the distance traveled. This area over here is the distance traveled, which is equals to half into x into t, half x t. So this is the correct answer, xt by 2. question 11, we are asked, we are given the following information that the student applied a force F to a rubber band and measured the corresponding extension del X as F was increased and decreased. So this is increasing force. This is when the force was increased and this is when the force was decreased. In part A, we have to state how the graph shows that the rubber band deformed elastically. Elastic deformation means that if you extend something and then remove the force, the particle returns to its original length. Here we can see that the rubber band returns to its original length with extension 0. So we can say that when the force is removed, the rubber band returns to its original length. Now for part B, we just said that the work done by the rubber band as F is increased is greater than the work done by the rubber band as F was decreased. There is a difference in these values because heating occurred. We have to determine the energy that caused heating as F was increased and decreased to 0. So you have to find this area over here bound by both of the curves. So we have to use approximation for this. I'll count with these boxes over here. So one of these box has an area of 0.5 into 0.5. So 0.25 Newton centimeter. So we need to count how many full boxes are here and in between this. So in between this and this, we have to find the number of boxes. So the number of full boxes are 1, 2, 3, 4, 5, 6, 7. I don't see any more. And the number of partial boxes are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We can calculate with this. So we'll have 7 plus 24 by 2 for the partial boxes times the area of each box, which is 0.25. We'll get, we can convert it to centimeters as here as well. So if we convert centimeters to meters, so if we have this, area of this will be 1 Newton into 0.5 newtons into 0.5 into 10 to the power minus 2 meters. We'll get 0.0025 joules. If we calculate this over here, we'll 19 into 0.0025 or 0.0475 joules. So change in energy would be 0.0475 joules. Now to question D. We are asked a question about darts. We have a description of the game of darts over here. And we're given this detail. So it's a question about projectile. We're given that it has a velocity of 15.6 meter per second at an angle of 5 degrees to the horizontal. We are given that the dart travels a horizontal distance d to the dartboard, and that just before the dart hits the dartboard, the vertical component of the velocity of the dart is 0. We are given that air resistance is negligible. We have to show that the time taken for the dart to reach the dartboard is about 0.14 seconds. We have to use the detail that the vertical component of the velocity of the dart is 0 just before the dart hits the dartboard, which means that when the dartboard was here, the dart was at its maximum height. At maximum height, vertical velocity is 0. So we can find the time for it. So we'll consider the vertical motion here. The initial vertical velocity is 15.6 sine 5 degrees. This is the vertical velocity, 15.6 sine 5.0 degree, and this is the horizontal component, 15.6 cos 5.0. The vertical acceleration is minus g because it's opposite to the direction of motion. So vertical acceleration is minus 9.81. We are also given that the final vertical velocity is 0 over here. Now we have to find the time. So we have everything except the vertical displacement. So we'll use v equals to u plus at. We have 0 equals to 15.6 sine 5.0 degrees plus minus 9.81, the acceleration, times t. T will be 15.6 sine 5 degrees divided by 9.81. If we calculate this, we'll get 0.1385, so 0.139 seconds, which is about 0.14 seconds. Now we have to find the horizontal distance d traveled by the dart. The travel time is 0.139 seconds. The horizontal velocity is 15.8 cos 5 degrees. Sorry, 15.6. Horizontal motion. So horizontal motion. So d will be 15.6 cos 5.0 degrees multiplied by 0.139. This will be 2.15 meters. Now moving on to question 13. We are given a toy called a Cartesian diver inside a sealed plastic bottle of water. This is the Cartesian diver over here. So it is a tube with trapped air inside it. We are given that the student squeezes the bottle, more water is forced into the tube, and the volume of the trapped air decreases, we have to explain why the Cartesian diver accelerates downwards. We have to consider the forces on the tube. So this is the weight of the tube, and this is the upthrust. If the student squeezes the bottle, more water will be forced into the tube over here. And if more water is forced into the tube, and the volume of air here will decrease. If we consider this, the upthrust is the volume of air times the density of water. If more water is forced into the tube, this volume will decrease, so the upthrust will decrease. So this is our first point. As the volume of air bubble decreases, the upthrust on the tube decreases. If the upthrust becomes smaller, we'll have a case like this. So this is the new upthrust. So there will be a resultant downward force. So there will be a resultant downward force downwards, and there will be a downwards acceleration. I can say so weight is greater than upthrust or vice versa. And hence there is a resultant downward force. Causing it to accelerate downwards. Now on to question 14. We are given that a child's slide has a vertical height of 1.7 meters. And the child starts from rest at the top of the slides and moves down the slide. The resistive forces are considered to be 0. And now we have to find that why equations of motion should not be used to determine the maximum speed of the child. And we are given this hint over here that we should consider the shape of the slide in this case. For using the equations of motions, we need a constant acceleration. So for using the Suvat equations, the criteria is acceleration must be constant. In the case of the slide, the acceleration will depend on the steepness or gradient of the slide. For example, on a ramp with a constant gradient, the acceleration is mg sine theta if this is theta. This would be the acceleration is g sine theta if there are no resistive forces. So ma is mg sine theta, the m's cancel out, we get m equals to g sine theta. However, for this ramp over here, we have one value of theta over here, another value of theta over here. So the sine theta is always changing. So this is not a constant acceleration for this ramp. So we'll say that the steepness of the ramp is not constant. So acceleration of the child is not constant as well. Hence, equations of motions cannot be used. Equations of motion cannot be used. As it requires a constant acceleration. Now we are given that the child has mass 24 kg and we have to determine the maximum speed of the child. For this we'll have to use energy. So as there are no resistive forces, the gravitational potential energy will convert into kinetic energy. The gravitational potential energy at the top is mg del h equals to half mv square. The masses cancel out at, so we'll have 9.81 into del h, which is 1.7 meters, and in this case we'll have half into Vmax square. So Vmax will be 9.81 into 1.7 divided by half, or you can say this multiplied by 2. So this is Vmax square. So Vmax will be root over this, which will come out to be 5.78 meter per second. Now moving to part B. We are given two slides, X and Y, which have the same height. Slide X is longer than slide Y. They have the same height. We are given that the child moves from rest down slide X and reaches a maximum speed of Vy, and the second child moves from rest down slide Y, reaching a maximum speed of Vy. Since the resistive forces acting on the children can be ignored over here, we have this. The GP of both children on the slide will be the same because on both slides the height is the same. So the GP, we have also this detail over here. Child on slide Y has a greater mass than the child on slide X. However, if we see that when GP is converted to KE, we have mg del h equals to half mv square. So this does not depend on the mass of the children. So m cancel out. So we'll have half v square equals to g del h. In both cases, the height del H is the same. G is also a constant. So for both cases, Vx and Vy both must be the same. So we'll have Vx will be equal to Vy. Since GPE or change in GPE in both slides are the same, and the maximum speed depends on the height only and not on the mass of the children. We can write the equation for safety. We can write here that mg del h equals to half mv square. Cancel the v's out. Show that v square equals to 2g del h and v equals to root over 2g del h. Now on to question 15. We have to, in part A, we have to state the conditions needed for Stokes' law to apply. We are given that a small ball bearings fall through a liquid, and we have to determine the viscosity. For Stokes' law, the conditions are that we have a laminar flow and the objects falling slowly. Another one of them is the object being spherical. Since we are given that there are small ball bearings, we are given that they are spherical, so we cannot state that over here. So our question will be our answer will be the ball bearings are falling at a low speed in laminar flow. Now for part B, we have to complete the free body force diagram. There is a drag force upward. We'll also have upthrust over here. So we'll add the weight over here. The upthrust plus drag should be somewhat approximately equal to the weight. We can just show the upthrust with another arrow or on the same arrow as well. So this is upthrust. Now we in part B2, we are given that the student thought that the liquid she used might be glycerol. She made measurements to determine the terminal velocity of a ball bearing, which came out to be 0.0824 meter per second. We have to find whether this was glycerol. We're given that the radius of the ball bearing is 2.3 millimeters or 2.30 into 10 to the power minus 3 meters. The weight is 4 into 10 to the power minus 3 and the viscosity is 0.934 pascal second. In this scenario, we have to use the equation weight equals to upthrust plus Stokes drag. The weight is given, so the weight of the ball bearing is 4.00 into 10 to the power minus 3. The upthrust will be rho Vg. The density. We can solve this in 3 ways. One of them would be to take the viscosity of glycerol to be the variable over here and then showing that this is the answer we get is close to 0.934. Another one would be to take the density of glycerol to be the variable and calculate that. Or we can do this. We can take the terminal velocity to be the variable and show that it's somewhere close to 0.0824. I'll do the last one. So taking the terminal velocity as the variable. The upthrust is rho Vg. The density of glycerol is 1.26 into 10 cube. The volume will be 4 by 3 pi r cube. So 4 by 3 pi into 2.30 into 10 to the power minus 3 cube times 9.81. So rho Vg plus the drag force would be 6 pi Rv at Rv. So 6 pi times the viscosity times the radius times the terminal velocity. I'll take the terminal velocity as the variable over here. We'll have 6 pi into 0.934 into 2.30 into 10 to the power minus 3 times V term Vt. Vt will be 400 into 10 cube, 4 into 10 to the power minus 3 minus 1.26 into 10 cube into 4 by 3 pi into 2.30 into 10 to the power minus 3 cube into 9.81 divided by 6 pi into 0.934 into 2.30 into 10 to the power minus 3. We'll get velocity, terminal velocity to be 0.0832 meter per second. So the values over here, 0.0824 and 0.083, they are very close to each other. So this is approximately equal to 0.0824. Therefore, so we can say that the liquid might be glycerol. We can write it's very close to the measured terminal velocity. Now in question number 16, we are given that a skittle is a wooden object that can stand on upright. So these are the skittles. Then we are given that in a game of skittles, a ball is thrown at some skittles to knock them over as shown. Now we are given a graph that shows the velocity of a skittle and how it varies with time. The time shown starts just before the ball hits the skittle. So if we look, this is the time at which the ball hits the skittle. So around here. So this is where the ball hits the skittle and this is where it starts to move. And the collision continues up until it reaches a constant velocity over here. Now in part A, we have to determine the average acceleration of the skittle during the collision. So if we do this, we'll have to find the average gradient. So something like this. The gradient of this line over here, let me do it in a different color. Something like this. The average acceleration would be the gradient of that line. So it starts somewhere over here. So let me consider this point. This is each small box would be 0.5 for 5 boxes, 0.5 for 5 boxes, so 0.1 per each box. So this value over here is 2.5, 2.6, 2.7, 2.8, so 2.85. We can take our values from here, so 0 and somewhere in between. So let's just take this in between. So this in the x-axis, each 5 box is 10 units. So each box is 2 units. So this is 12, this is 14, this is 15. This value over here is 48. So the acceleration equals to the gradient, and that is equal to 2.85 minus 0 divided by 48 minus 15. Now in y-axis the velocity is given in meter per second, however the time is given in milliseconds. So we'll have to convert that back to seconds by multiplying 10 to the power minus 3. So we'll get a value of 86.4 meter per second square for the acceleration. Now we have the 6th marker here. We have to explain how Newton's second and third laws of motion apply to the ball and the skittle during the collision. Here, the ball is applying a force on the skittle. So the ball impacts the skittle and exerts a force on it, causing the skittle to accelerate. The skittle, according to Newton's third law, will apply a equal and opposite force on the ball, causing the ball to decelerate. So that's about Newton's third law. That's all the points about Newton's third law. Now we have to go and think about Newton's second law. Now if we go and see, since the ball is exerting a force on the skittle, this is an unbalanced force. It's not balanced by anything over here, which causes the skittle to accelerate. And the force that the skittle exerts on the ball causes the ball to decelerate with this unbalanced force over here. This causes resultant forces or unbalanced forces. Causing the skittle to accelerate. Causing them to accelerate according to Newton's second law, which states that this is Newton's second law. Hence, the skittle accelerates and the ball decelerates. Now moving to part C. The ball is thrown again and collides with another stationary skittle. During the collision, the horizontal velocity of the ball changes from 7.2 to 1.6. The horizontal velocity of the skittle immediately after the collision is 3.1. We have to determine the mass of the ball. In this, we'll use conservation of momentum. So this is the skittle of mass 1.4 kg. This is m kg. This is the ball. The initial speed of the ball here is 7.2, and for the skittle it's 0. The final velocity is 1.6 in the same direction, and for the skittle it's 3.1. So using conservation of momentum, m into 7.2 equals to m into 1.6 plus 1.4 into 3.1. We'll move the m's to the left, so 7.2m minus 1.6m equals to 4.34. So we'll get m equals to 4.34 divided by 5.6, which is equal to 0.770 kg. My bad, this will be 0.775. Now on to question 17. A student determined the Young modulus of a material in the form of a wear. The student used a micrometer to measure the diameter of the wear. We have to describe how the student could check that the wear is uniform and check that the wear has a circular cross section. To make sure it is uniform means that the wear has a consistent thickness. A non-uniform wear would be something like this: thin over here, thick over here. So to show that it's not uniform, the student should measure the diameter at several positions. So you measure the diameter here, 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 and check if they're constant. So measure the diameter at several positions. Now in this part over here, we need to check that the wire has a circular cross section. So a cross section like this. If it was a circular cross section, the radius you calculate over here, the diameter you find over here, here will all be equal. However, if it was something like this, a rectangular shape or even a square, if you measure the diameter from here, you will find one thing, and if you measure from the diagonals, you will find one thing. So to check if it's circular, we have to check if the radius is constant across all alignments or orientations. So we have to measure the diameter. So this to measure, this to ensure that the wire is uniform, and this point to ensure that it's circular. Now we are given that the student hung a reference wire and the wire being tested from the ceiling. So this is the wire being tested and this is the reference wire. He then added masses to the mass hanger. So this mass hanger over here, and measured the corresponding extension. The initial reading was 100 gram and 0.0 on the vernier scale, so this has no zero error. In part 1 of this, we have to explain one other safety precaution. We are given one of them, which is he kept his feet away from the apparatus so the mass couldn't fall on his feet. Since we are using wires over here, the wires might snap and hit our eyes, so we'll have to wear goggles in this case. So safety goggles should be worn. Because the wire could break or snap. Now we are asked that each time the student added more mass, del X was increased by a few millimeters. We have to explain why he should measure del X using a vernier scale instead of a meter rule. We have to answer this with respect to the percentage uncertainty. We know that the vernier scale has a better resolution. The resolution of a meter rule is 1 millimeter, whereas for vernier scale it is 0.1 millimeter. So the vernier scale has a better resolution of 0.1 millimeter, which would decrease the percentage uncertainty. In the value of del X. Now for part C, for each mass added, the student determined the force on the wire and plotted the graph below. We are given three materials: aluminium, brass and steel, and we have to determine which material the wire was made from. We are given the original length of wire 1.8 meters and diameter of the wire 0.17 millimeters. This is an extension against force graph, so its gradient would give us lines now. So we find the gradient over here. The value of y value would be, okay. So 10 small boxes are for 2 units. So 2 units represented by 10 small boxes. So each small box is 0.2. So this is 10.2, this is 10.4. And this is 15. In the x-axis, 5 units are represented by 10 small boxes. So each small box is 0.5. So this is 0.5, this is 1. So the gradient is 10.4 minus 0 divided by 15 minus 1. Now here the extension is given in millimeters. We have to convert it to meters by multiplying 10 to the power minus 3. We'll get a gradient of 13 by 17,500. This is extension by force. So force by extension will be 1 by 13 by 117,500, or this is F by del x, or the steepness. Now we have to find the Young's modulus. The Young's modulus is equals to the stress divided by the strain. Stress is force per unit area and strain is extension per unit length. So we'll have F by A equals to del x by x have Fx by del x A. We know F by del x, we have calculated that, so I'll separate that here. So F del x times x by A. X is the original length of the wire, A is the cross-sectional area. We know F by del x to be 17,500 by 13. We are given the original length, which is 1.80, and the cross-sectional area will be pi r square or pi d by 2 whole square, which is 0.17 into 10 to the power minus 3 by 2 squared. So we'll get answer of 1.06, 1.07 into 10 to the power 11 Pascal. If we convert it into gigapascals to match with this, we'll get 1.07. To convert this into gigapascals, we'll just multiply 10 to the power minus 9. We'll get 107 gigapascals. This is closest to this value over here. So the material should be from brass. So 107 gigapascal is basically almost equal to 106 gigapascal. So the wire is made of brass. Now moving to question 18. We are given that a uniform door of width W is supported by 2 hinges X and Y. X and Y are a vertical distance L apart as shown here. We have to state the conditions for the door to be in equilibrium. For something to be in equilibrium, must have zero resultant force and zero moment. So there must be no resultant. There must be no unbalanced or resultant force. Or resultant. You can write either one. And the resultant moment about any point should be zero. Now we have to give the meaning of the term center of gravity. Center of gravity is the point through which all of the weight of an object acts through. This is the definition of the center of gravity. In part C, we have to use the following information to calculate the horizontal component of the force of hinge Y and show that it's about 40 newtons. So this length L, we are given this is 1.60 meters. W is the distance or the width of the door. This is 0.85 meters. So the center of gravity will be somewhere over here. This will be 0.85 by 2 or 0.425. This distance over here will be 0.8 meters, half of the distance from X to Y. So we can find this angle over here by drawing a triangle. So this, if we draw a triangle, this will be something like this. This is 0.425. This is 0.8. This is theta. So tan theta would be 0.425 by 0.8. Theta would be 27.979. Now we have to show the vertical force by X and the vertical force by Y will be the same. So each of that will be half of the weight. So the force on Y vertically, or the vertical force force by Y will be half of the weight. The weight is 14.4 kg. So 14.4 into 9.81 divided by 2. Force on Y, if this is force by Y, the vertical component of that would be Fy cos theta. So Fy cos 27.979 will be 70.4 0.632. So force by Y will be 70.632 by cos 27.979. So the horizontal component of Fy horizontal will be 7 Fy sine theta. So Fy is 70.632 by cos 27.979 into sine 27.979. So we'll get 70.632 times 1027.979. You don't need to find this over here, we can just put the values in. So 70.632 times, we know the exact value of this, 0.425 by 8. 0.425 by 0.8, the value of 1027.979. So we'll get a value 37.4 newtons, which is approximately 40 newtons. Now in part 2 we have to find the force F. Now in this question we have to find theta and the value of F, which is Fy. We did half of the calculation over here. We already know the value of theta and the value of Fy. So we'll just do that again. We'll show that this is the center of gravity. This is 90, this is 0.425, this is 0.8. So tan theta would be 0.425 by 0.8. So theta is 27.9 degrees or 27.98 degrees, or in 3 significant figures we'll just write 28.0. We know F horizontal from part A, which is 37.4 newtons, and F vertical will be the weight of the door, so 14.4 kg into 9.81, so the weight divided by 2. So the force on Y would be root over 37.4 squared plus 14.4 into 9.81 by 2 whole squared. We'll get 79.9 newtons. So F is 79.9 newtons and theta is 28.0 degrees. In part 3 we have an identical door that is supported by hinges that are closer together. We have to write down what and explain what the effects of this new value of L would change F and theta by. So this was our door. So instead of the hinges being here, the hinges are now here. So instead of being over there, the hinges are here. So the forces are acting on this line. So the value of theta increases. If you notice, the value of theta increases. So the value of F sine theta would increase because the graph of sine goes like this. However, the value of f cos theta would decrease since the graph of cos theta is like this. So we can write the change in theta. We'll also have to mention the center of gravity. Since the center of gravity is still 0.4 to 5 meters away horizontally, we'll write moment of now we see that the horizontal component of the force increases because theta is becoming larger. We'll write that. And the vertical components must be the same because each of the hinges must hold the same force. So the vertical component of force remains constant. Therefore, theta increases and f increases. The f must increase because we have to keep the same value of f cos theta. We have to keep the same value of f cos theta with a lower value of cos theta. So f cos theta is constant and cos theta becomes smaller. So if cos theta becomes half of what it used to be, the force must be twice of what it used to be be constant. That's it for this paper.